In this video, we're going to take a look at polar form of complex numbers. We're going to look at plotting numbers in the complex plane and finding the modulus and argument of a complex number. So the complex plane, very similar to your Cartesian or rectangular xy plane from algebra class. So we have points xy in your Cartesian plane, represented by z equals x plus yi in the complex plane. So x is called the real part and y is called the imaginary part, since y has the imaginary unit I attached to it and x does not. So x is your real part and y is your imaginary part. And we plot points very similarly in the complex plane as how we plot them in the Cartesian or xy plane. So our point z equals x plus yi, going to go over x units and up y units. And this depends on whether or not, again, x and y are positive or negative or 0. So no different than plotting the point x comma y that you've done many times in the past. So now we're going to find the modulus and argument of a complex number. So the modulus is simply the absolute value of it, and it denotes how far that point is from the origin. So you're calculating how far from the origin you've gone, if you've gone x spaces outward and y spaces up or down. So your modulus of z, absolute value of z, is the absolute value of your complex number, which is just the square root of x squared plus y squared. And notice here we do not incorporate the I in there, where I squared would equal -1. So only the real part squared plus the imaginary part squared. Do not include the I when finding the modulus of a complex number. So again, if we connect our point to the origin, it's going to model an angle drawn in standard position. So here we have, in the first quadrant, z equals x plus yi. X and y are both positive in the first quadrant. If we connect that point to the origin, it's going to make an angle theta in standard position. And if z is in polar form, then that total angle that was rotated is called the argument of z. So the angle of rotation called the argument. So the set of all possible arguments for z is denoted argz with a lowercase a, and these could be found by using coterminal angles. So as we just rotate another 360 degrees or 2 pi radians in any direction, both forwards and backwards, we get the exact same point through coterminal angles. So the set of all those arguments, all those possible angles, is argz, where arg is lowercase. And if z is not 0, but your rotation angle between negative pi and pi, well, greater than negative pi but less than or equal to positive pi, then theta is the principal argument of z and is written argz, where arg now is capitalized. So that's the difference between lowercase and uppercase. Is uppercase is specific to this interval, greater than negative pi but less than or equal to pi, whereas lowercase r is a set where we can use coterminal angles to get the values. Kind of similar to how we used plus 360k or with sine and cosine when solving trig equations. We can get the total angle rotated via reference angles using theta prime is inverse tangent of y over x. We'll take the absolute value for our examples here, and then figure out what quadrant we're in, how many total degrees or radians we rotated. So let's take a look at some examples. Example 1, plot each complex number, find its modulus, the real and imaginary parts, and argument, the regular argument and the principal argument of z. So don't necessarily have to go in order. So looking at the real part of z first is square root of 3. Imaginary part of z is -1. So if we can imagine this is square root of 3 minus 1i, we get square root of 3 for the real and -1 for the imaginary. Here's the point plotted. So we go over radical 3 units on the x-axis and down 1 unit on the imaginary or y-axis. And it's just like plotting the point radical 3 comma -1. And if we find the distance that point is to 0, that is the modulus, or that point is to the origin. So we had to go radical 3 units out and 1 unit down. So radical 3 squared plus, I advise using positive values here when when the coordinates are negative. But radical 3 squared is 3, plus 1 squared is 4, so the square root of 4 is 2. So this is a distance of 2 from the origin. So a tip that I'll go is I'll find the principal argument here, capital arg, first, and then use that to find the general solution, lowercase arg. So you don't have to do that, but that's just the order I go in. So again, we're looking at this angle right here. If we draw this in standard position, we got a negative angle, so it should be somewhere between negative or 0 and negative 90 and 0, or negative pi over 2 and 0. So to get that, we use inverse tangent. It's a 30-degree angle, so negative 30, which gives us negative pi over 6 for the angle of rotation. And then if we look at coterminal angles, negative pi over 6 plus every 360 degrees or every 2 pi radians thereafter. And k could be a positive integer, negative integer, or even 0. So if k is 1, that would be a coterminal angle of 11 pi over 6, which is this total amount rotated there. It'd be 11 pi over 6, which is negative pi over 6 plus 2 pi. But for this one, the negative pi over 6 is greater than negative pi, but less than or equal to pi. All right, example 1b, negative 2 plus 4i. The real part is negative 2. The imaginary part is 4. Here it is in the plane. So negative 2 plus 4i. So the point, same as the point, negative 2, 4. If we find the distance, it's out 2 units and up 4. So 2 squared plus 4 squared is 20. And square root of 20 is 2 times the square root of 5. So distance to the origin, 2 times square root of 5. Arg z, again, inverse tangent of y over x, so 4 over negative 2 is, if we took the absolute value, it'd be 63.4 degrees. But since it's in quadrant 2, if we put that 63.4 degree reference angle in quadrant 2, the total angle rotated is about 116.6. So if we connect this to the origin, then the total amount that terminal side would have rotated is about 116.6 degrees. The exact value that the book says is pi minus inverse tangent of 2, which is 180 degrees minus that 63.4 degrees. So as far as exactness goes, it's pi minus inverse tangent of 2. So there's a lot to be said about approximation as well. So our argument for z is pi minus inverse tangent of 2. And if we just take that and add 2 pi k to it, we'll get our arg z lowercase. Right. Example 1c, we got z equals 3i, or 0 plus 3i. So the real part is 0 and the imaginary part is 3. This corresponds to the point 0, 3, which is on the y-axis. That has a distance of 3 to the origin, which is really handy if it's on an axis, because you can just count how far away it is without having to use x squared plus y squared, although you'll still get 3. Our argument is pi over 2. It rotated 90 degrees, or pi over 2 radians. And our principal argument is pi over 2. And then the set for the argument is pi over 2 plus 2 pi k. So just more coterminal angles. All right, finally, example 1d. We got z is negative 117, or negative 117 plus 0i. So negative 117 is the real part. Imaginary part is 0. If we graph this, here's what it looks like. It is 117 spaces away from the origin, so that's its modulus, is 117. And it had to rotate 180 degrees, or pi radians, in order to get there. And then our set of general angles using coterminal angles is pi plus 2 pi times k. All right, that about does it for this video. I hope you found it educational, and I will see